We need to solve the system of three equations with three variables. I've numbered the equations with Roman numerals 1, 2, and 3 so that I can write down a plan and keep my work organized. When your equations start to have three different variables in them, you very often need to keep your work organized or you're going to get lost in the middle of it. Another thing is, I don't know about you, but when I'm copying these kinds of equations down from a book to a paper or something like that, I tend to make mistakes in the copying. So I double-checked this before I started because I don't want to spend the time that I need to spend on this problem if it's the wrong problem. So it looks like the y's have a 3 and a 2, a negative 3y and a 2y, and the x's and the z's just have 1's and 2's, so I'm going to stick with 1's and 2's, and I'm going to focus in on the x's. So I'm going to combine these two equations, equations 1 and 2, in the following manner. I am going to take the first equation, and I'm going to multiply it by negative 2, and then I'm going to add the second equation. Now, if you think about this plan, think about the x's. In the first equation, there's just an x, and so this will be negative 2x. In the second equation, there's a positive 2x, and when we add those, the x's are going to disappear, and this is going to give us an equation in y and z. And then I'm going to do it again with the different two equations and get another equation in y and z, and then I'll have two equations with two variables, and I'll know how to do that from previous sections. So let's do this plan right now. So I'm going to distribute negative 2 throughout this top equation. So I'm going to distribute the negative 2 on both sides. So that's going to look like this. And then I'm going to leave this second equation alone. So when I distribute the negative 2 through, I get negative 2x plus 2y plus 2z equals 0 times negative 2 is 0. Now I'm going to copy down the second equation. And then I'm going to add. And then I get minus y plus 4z equals 7. So now I'm going to invent a plan that uses these two. It's going to be equation 2 plus 2 times equation 3. If you focus on the x's, this will be 2x. This will be negative 2x, and when we add those, we get 0 x's, and we'll have our second equation in y and z combined with our first one, and then we can put those two together. So let's get started with the plan. We have 2x minus 3y plus 2z equals 7. And then we got to distribute a 2 through this one. So I'm going to have a negative 2x, and my x's are working out as planned, plus 4y plus 2z equals 2. Now I lost my concentration in the middle of that, so right now as I'm talking, I'm going back and checking, and I think that I've done it correctly. So I get y plus 4z equals 9. Now I have these two equations, and I'm going to write them down again because I like to keep my work organized. It makes me feel like I'm maybe doing okay. Here, when we add, we see that things are lined up nicely, and 16, not 18. And that is really nice because z equals 2. So, you know, we have an x, y, z kind of an answer. So in that answer, we have z equals 2 already. And if we go back to one of these two equations, I don't care which one, I'll go back and substitute the z equals 2 in here. And we get y plus 8 equals 9. Subtract 8 from both sides, and we're getting y equals 1. I've lost my pen color, so I'll get it back eventually. We have y equals 1. And then I'm going to go back to this very first equation, x minus y minus z equals 0, and I'm going to put in y and z. So we have x minus 1 minus 2 equals 0, x minus 3 equals 0. Add 3 to both sides, x equals 3. So it looks like we have the solutions x is 3, y is 1, z is 2. That's one solution. And we could check it. I'm not going to check it for you, but we could check it by testing, by putting in 3, 1, and 2 here, here, and here in the first equation and see if we get 0, and putting 3, 1, and 2 into the second equation and seeing if we get 7, and putting 3, 1, and 2 into the third equation and see if we get 1. If all three of those equations check, then we've proven that this is the correct answer. This is a lot like the last problem. I've written the equations down, double-checked them, pardon me, and I've named them with Roman numerals, and I've created the two plans. These plans are focused on z's. So for instance, if you look at the z's in the first equation, it's minus 3 of them. If you look at the z's in the third equation, this will be plus 3 of them, and when we add, we'll get 0 z's. So let's get started with that plan. We're going to start with the first equation. And we're going to add to it the third equation, but a negative 3 distributed through. So I'm going to write down that negative 3 so I can look at it. Notice my z's are working out famously. And here I'm getting minus 2y's. And here a strange thing happened. I got 0 z's. Didn't really expect that to happen, but it did. So that's okay, but I wasn't expecting it. So now let's go ahead and do the second plan. And it is 2, equation 2. And then plus 2 times equation 3. And so I am going to kind of ignore that one, and I'm going to put a 2 over here so I can see when I distribute the 2 through, I get 2x's plus 4y's minus 2z's. Those z's are working out well. And this time I get 3y's equals negative 1. So what do we have here? Well, the z's disappeared, but I forgot my 7x. So maybe I was carried away by the x's disappearing over here. So now I have two equations. I expected them to be z-less, and they are without z's. But this one is also without x's. So at first glance, I'm not sure what to do because I was looking for two equations with x and y in them. But this is actually better. If we divide both sides by negative 2, we're going to get y equals negative 5. And that's a pretty nice thing because that tells us our y value in our solution. You know, this is the x and the y and the z, and so the y value is negative 5. And over here in our second equation, if we put a negative 5 in for y, if we substitute, we ought to be able to figure this out pretty well. Adding 15 to both sides and dividing both sides by 7, we have x equals 2. And now armed with x is 2 and y is negative 5, we can go back to any of the first equations. It doesn't really matter. I'm going to use the second one just because I want to. So we have 5 times x, which is 2, minus y, which is negative 5. Notice that's minus a negative. That's a little tricky. Plus 2z equals 3. So 10 plus 5 plus 2z equals 3. 15 plus 2z equals 3. 2z equals, subtracting 15 from both sides, we get negative 12. Dividing both sides by 2, we get z equals negative 6. So we have the solution 2, negative 5, negative 6, and that would check if you took the time to check it. So in problem 15, I wrote down the three equations. I labeled them 1, 2, and 3 with Roman numerals. I created a plan that was focusing on the x's. I executed the plan here and found out that not only did x's disappear, but so did z's. And I found y equals negative 3, and I was feeling pretty proud of myself. Then I followed up that plan by combining equations 2 and 3 in this way so that that would also get rid of the x's, but it also got rid of the z's, and so I ended up with negative y, or the opposite of y, equals -1, took the opposite of both sides and got y equals 1. Now this says y has to be 1 and only 1. This says y has to be -3 and only -3. There is no way we can have a solution that has both of those. They're contradictory. So there are no solutions in problem 15. And that's what I think you ought to write. No solutions or no solution. So again, I carefully wrote down the 3 equations. I numbered them with Roman numerals 1 through 3. I made a plan that would get rid of x's, and my plan used equations 1 and 2 in this manner. And I did that here in equations 2 and 3 in this manner. And I did that here. I took my two variable equations, added them together, all excited that the y's would disappear, but then so did the z's and so did the number. So I got 0 equals 0. Now here's the clue on what this means. 0 equals 0 is true no matter what y is, and no matter what z is, and no matter what x is. So what this is trying to sort of tell us is, this is true often. This is true for lots and lots and lots of triples of numbers. And we could find some of those triples of numbers. We would find an infinite number of answers where x was a specific number and so was y and so was z. We can find an infinite number of them. But for this course, we're just going to say either that there's an infinite number of solutions, which is kind of an okay answer in my opinion, or we're going to put that it's dependent. That's what the book wants, that they're dependent, and that's just a way of describing this situation where there's more than one solution. And we're not going to go any further with that in this course. So if you want to use dependent, you can, but when there's no variable at all, when everything cancels out and you get a number equals itself, that's true often, is you'll just put dependent and be done, and that's it.